So Wendy, we start recording. I'm going to give a. Okay, so hello everyone. I'm Shiliang Shan from Royal Military College of Canada. So while we meet online today, I would like to begin. Let me stop this. While we meet online, I would like to begin by acknowledging the indigenous peoples of all the lands that we are on today. So welcome to the coastal oceanography and the inland water sessions. So we have many interesting presentations today, and they are divided into 3 parts. I will be chairing part 1, and Guoqi Han from DFO will be chairing part 2 and part 3. Part 1 focuses on the coastal oceanography studies over the west coast of Canada. There are 6 15-minute presentations as listed on the screen. Our first speaker is Professor Jody Klymak from University of Victoria, who will going to talk about the ventilation of fjords by down-fjord wind. So now let us welcome Jody Klymak for his presentation.
Good, thank you, Dan. Just getting the sharing set up here, I think. Okay, so hopefully you all can see my presentation. If there's any problems, just let me know. What I'm talking about today is what happens when wind blows down fjord. And so this is a simulation. And I'm also going to be talking about simulations today. Here's the head of the fjord, this is the ocean side, and the wind blows from the head of the fjord down inlet. The simulation is going to restart in just a second here. We're about 200 meters depth, and this is about 140 kilometers in width. So what happens when the wind starts blowing is it pushes all that fresh water out of the fjord, and then you start ventilating this deep water. And then when the wind stops, the fresh water comes back in, you get a complicated seiche that sets up, and you end up, what we're interested in is this pocket of higher oxygenated water that gets down to about 100 meters. And so that has obviously implications for the health of the fjord, and we'd like to be able to predict that. So the motivation for this comes from a study that Jen Jackson did looking at Butte Inlet. So this is a picture of Butte Inlet here. And this is a CTD section taken in January of 2019, and then a second CTD section taken in March. And we're kind of looking at the same sort of scales. It's flipped around though this time. So this is the head and the ocean is on the left in this picture. And you see some pretty big changes between these two cruises, getting down to about 100 meters. It got much colder. And then this is oxygen. You see it became much more oxygenated. So we're able to get oxygen down to 100 meters. Something happened between those two cruises. And what happened is important for oxygenation of the fjord. It's important for exchange of nutrients in the fjords, which is obviously important for biological productivity. And cooling of the fjord sets the annual cycle. We also know that the exchange in fjords is important for glaciated fjords. We're not looking at a glaciated fjord, but people have done similar studies where they're interested in how much heat manages to get into the fjord due to these sort of wind-driven upwelling processes. And there's a very nice paper by Spall. And that has obvious implications for trying to understand melting at the base of the fjord. Okay, so what did I do? We ran these simulations. This is the picture of that simulation that I was showing you. And this is velocity, and there's depth to 200 meters. And I've got it flipped from Jen's pictures, where you've got the land on the left and the ocean on the right. And this is oxygen over time in that fjord. And then this is just a plan view showing you the model domain. There's a control section. There's a big receiving domain. And then the wind, in this case, I allowed the wind to have a spatial structure. So the wind tails off. These are thought to be katabatic winds that blow down the fjords. And there's some hint that they might lose their wind strength as they blow down. And then this is just a picture of the control section. One thing about these forcings is that there's no heat forcing. Okay, so I just have wind forcing in these simulations, and then I have realistic oxygen atmospheric exchange. We did do some runs with heat forcing, but it doesn't change the results very much. Okay, and then my argument is that this ends up looking a fair bit like what Jen sees. This is I flipped her pictures around. This is the head of the inlet. This is the ocean, and you get this high oxygen going to about 100 meters or so. And here we get this high oxygen going to 100 meters. If we stop the wind, then the wind has been blowing. Now you stop the wind and you get this seiche that goes through, and you get this water being resubducted. You get the fresh water comes back on the surface. This water gets resubducted and you end up oxygenating down to about 100 meters or so. As you can see, the sort of spatial scales are not dissimilar either, 50 or 60 kilometers. This gets to be 50 or 60 kilometers where you've reoxygenated. So we think that this is kind of an important process for these fjords. And we think we do a reasonable job of stimulating them. So this leads to a whole host of questions that then I want to explore a little bit more fundamentally, and this includes, how deep are we able to get to? So given how strong the forcing is, given what the stratification is, how deep are we able to ventilate to? That's an obvious question. And then it also matters how long it takes to get to these depths. So these katabatic winds, they blow 3 days, 7 days, they blow for a while. But if it takes 100 days to get down to this sort of depth, then that's not very useful. This snapshot is actually 8 days. So to get into steady state, this simulation takes about 8 days to get into a steady state. And then some secondary questions are how much exchange do we expect to have happen due to this forcing, and how important is mixing to these tracer budgets? Does mixing dominate some of this injection of oxygen into the deep water, or is it all just air-sea gas exchange? Okay, and people, of course, have thought about these sorts of problems, particularly with respect to lakes, though some of this work has been applied to fjords, particularly by David Farmer, who did a really nice study back in the 70s on this. And, the idea behind what's called the Wedderburn number is that you've got a wind stress blowing that pushes water offshore. You develop a sea surface tilt that counteracts the wind stress, and so you get a force balance between the wind stress and that sea surface tilt. And then the deep layer, you get a countervailing pressure balance between this interior tilt, between this upper layer and the sea surface tilt. And so this water ends up in steady state as well, and ends up being stagnant. And so that's kind of the simple idea behind that. And then, the idea of the Wedderburn number gets less than 1, then this deep layer sticks out, and you end up getting deep ventilation of that deep layer. And you can also get a time scale from those sort of same arguments. However, these questions that I asked just a second ago, they're not really two-layered questions. We want to know how deep it gets, not whether a supposed surface layer gets to the surface or not. And so what we did was we did a study where we systematically, same sort of setup, ran through a whole bunch of constant stratification, not two-layer cases where now this stratification is constant. And then we run these to a steady state, and we had various wind forcings that we used. And so this is an example of one of those runs. And again, you can see the fresh water gets pushed out early in the run. After 2 days, you start deepening this layer and drawing water up to the head of the inlet. And it takes about 8 days, 10 days. Certainly by this point, these two snapshots don't look that different, where you've developed a 100-meter deep sort of mixed layer, but due to the upwelling caused by the wind divergence at the head. So then all I did was I just did this for a whole bunch of different wind stresses and a bunch of different stratifications. So here you can see increasing wind stress, and you get what you expect as the wind stress increases, that you end up, this purple line is the densest water, the densest isopycnal that makes it to the surface in the inlet. And so that's what I'm calling the upwelling depth. And it gets deeper as the wind stress goes up. So this is 0.1, 0.4, 0.9 newtons per meter. Similarly, the opposite happens as stratification goes up. You're not able to get as deep, but hopefully that makes sense. So when you've got weak stratification, you get deeper, and strong stratification, you get shallower. So that sense of things makes sense. There's also a second important factor, which is how long the fjord is or how long the wind scale is. So I was able to vary those as well. So these are all the same stratification and wind forcing, but change the scale of the wind. So the wind dies off on a shorter scale here, medium scale, longer scale. And you see that as the scale of the wind gets longer, you end up ventilating more of the water. Similarly, here where you've got the where you change the length of the fjord instead of changing the length of the wind. Now this is the mouth of the fjord, this is the mouth of the fjord, this is the mouth of the fjord. And the longer the fjord, the deeper that you get as well. So that's nice. Whoops. If you also vary the water depth, then, so that's, another free characteristic, sorry. If you vary the water depth, then you find that there's really not much variation in terms of how deep things get. So this does not depend on the water depth. Okay, so just to summarize all that, as the water, as you get stronger winds, weaker stratification, D goes up. As it goes longer, then that increases. And so we're able to encapsulate all of that by plotting a whole bunch of these as time series. So what's on the x-axis here is time, and what's on D is that depth that we get to. And you see that as you go along in time, the mixed layer gets deeper and deeper, and then you get this basically a whole bunch of different forcings and a bunch of different stratifications. And then on the right side, I'm just varying the wind and or the length of the wind and the length of the fjord at different forcings. And then we came up with a scaling where you could say this depth is proportional to the wind stress cubed, or to the 1/3, the length of the 1/3, and n squared inversely to the 1/3. And the time scale also varies in a similar sort of fashion. And when you use that scaling, you get a very nice collapsing.
Quick reminder, 2 minutes remaining.
All right, thanks, Dan. You get a very nice collapse of the response in time and in depth, and using this scaling. So that kind of says that there's a simple explanation for that scaling. And indeed there is. If you take this same sort of idea that people use for one layer, but now you let your one layer be a different thickness, depending on the wind strength, then you can get this exact same scaling and this exact same power loss. So it's the same idea. The wind stress gets distributed over the depth of this layer. You've got a tilt of that isopycnal, and that gives you a scaling that gives you this 1/3 power. And the same happens, instead of it being a mode 1 wave that travels at square root G primed H1 or something, it's now scaled by a G prime that has to do with how thick that layer is. And so this is the scaling that you get. Okay, and so then again, this just collapses things quite nicely. Okay, so very briefly, I wanted to also talk about the amount of exchange, and we're able to run it with oxygen exchanging with the atmosphere. And if you look at that, then you find that this cyan line here is after 5 days of the wind blowing, and then we let the wind go and let everything settle down. And you see that there's very little mixing of that oxygen down. You see that the distribution of the oxygen is mostly set by whether you've got contact with the surface of the ocean and basically just mixing in that mixed layer. Similarly, when you think about net exchange, this is important for whether you bring heat to the head of the fjord for melting a glacier or something like that. Yeah, you get an exchange that happens, but very little of it's irreversible. While there's lots of violent seiches that go back and forth, the water mostly sloshes in, mostly sloshes out, and there's not very much that ends up being left behind. Okay, so then these are my findings, and just start the movie again. So basically, we're able to come up with a relatively straightforward scaling for how deep the water is going to be coming up. I didn't show this, but if you do this with variable stratification, that works as well with minor adjustments. We do get oxygen exchange to 100 meters, but it's mostly dominated by ventilation. So this process that we're interested in versus mixing of ventilated water down. And the net exchange is modest. And finally, for further work, we're working with Hakai. We'd actually like to witness this happening in real time. And so Wiley Evans at Hakai Institute is helping us put out buoys and wire walker moorings, and we're trying to see this process happening. This is just an example of the data that we're able to collect with this wire walker. This is not in Butte Inlet, but hopefully we'll be doing that in the next couple of years. So we're looking forward to that. Okay, thank you.
Thanks, Jody. We have about 1 or 2 minutes for questions. For the viewer online, please feel free to type your questions online in the Q&A box. So Jody, I got a very quick question about the effect of bathymetry and tides. So what's your thought on the effect of very shallow seal and also the background tidal mixing, suppose if a fjord has very strong tidal mixing?
Yeah, Butte Inlet's actually Butte Inlet is actually quite deep, and so the tidal forcing is thought to be relatively modest, and it actually doesn't have much of a sill. So this is maybe thought to be more of an idealized situation. I think it's an interesting idea if you're trying to push all that fresh water out, and it's got to get over quite a shallow sill, then that's going to introduce a hydraulic control and might make it harder to get that water out. Now, the other thing I didn't really say, the irreversibility of things. I have a downstream condition that has an infinite supply of that fresh water. If your actual fjord has fresh water and it's spitting out into a place that's saltier, for instance, it's possible that plume could disappear and then things would be irreversible. You'd have shoved that water away and mixed it presumably in the larger receiving basin.
Yeah, thanks, Jody. And I think it's time to for our next speaker, Ben O'Connor, and he is from UBC, and then he's going to talk about the wind-driven process over Queen Charlotte Sound. Over to you, Ben.
Great, thank you, Dan. Great, thank you very much. Good morning, everyone. My name is Ben O'Connor. I'm a master's student at the University of British Columbia, supervised by Stephanie Waterman and working with my collaborators listed here. Today, I'm not going to talk about this long title. Instead, I'm going to talk about drivers of intermediate depth water property variability at the shelf break of Queen Charlotte Sound, British Columbia. So the study area is Queen Charlotte Sound, which is located on the coast of British Columbia, shown in the map here, to the north of Vancouver Island and the south of Haida Gwaii. The boundaries of the sound are shown in the dotted red line there. It's a highly productive area. It's an important pathway and feeding ground for migrating salmon, birds, and marine mammals. And it's also an interesting oceanographic environment due to its complicated bathymetry. As you can see, there's a number of large submarine troughs and banks that bisect the continental shelf. And this connectivity with the open ocean and adjacent inland waters promotes a wide range of interesting physical processes. So it's an interesting place to study. This work aims to address a knowledge gap that exists for the sound, specifically the lack of near continuous time series measurements and wintertime observations. So very quickly, the research goals of this project are to, one, investigate the spatiotemporal variability in water properties by analyzing 6 years of near continuous mooring data from the shelf break and nearshore regions of Queen Charlotte Sound. 2, aim to examine the role of advection and coastal downwelling in driving this variability on seasonal and subseasonal timescales. And 3, we aim to consider the implications of this variability for ecosystem conditions, both now and in the future. The primary data set for this work comes from a set of ocean moorings that have been deployed from 2016 until the present. The first I'll refer to as the nearshore mooring, which is located near the head of Goose Trough here, near the coast, at Station Hack 1. It's equipped with sensors deployed at 5 different depths listed here. Really quickly, is my pointer working on this slide?
Yes, it's working.
Okay, perfect. And the second one is our shelf break mooring at Station Scott 2, located at the mouth of Goose Trough, just adjacent to the shelf break here. It's in deeper water than the near shore, with sensors deployed at the depths listed here. Both moorings are equipped with a variety of CTDs, oxygen sensors, and acoustic Doppler current profilers, which allow us to record measurements of temperature, salinity, dissolved oxygen, and current velocity. Really quickly, I'm not going to make anyone look at this. This is just an example of the really rich data sets that come from these ocean moorings. I'll focus in just a moment. You don't need to look at this, but I will point out that throughout this presentation, I'm going to be referring to winter and wintertime, which I somewhat arbitrarily define as from November to April. So it's a 6-month winter. And in all my plots, I use this black or this blue shading to denote the winter time. And it's just an example of the shelf break time series. But I'll skip you the trouble of having to look closely at those and just tell you about this unusual subseasonal wintertime pattern that we found at the shelf break at 100 meters depth. And that's what I'm going to focus on today. So these plots here of density, oxygen, temperature, and salinity are for the shelf break mooring at 100 meters depth. The mean composite annual cycle for the full data record is shown in the colored lines. And then behind that in gray, I've plotted each of the individual years on record. And a quick overview of what this wintertime pattern is. It's characterized by these large subseasonal fluctuations on timescales of days to weeks during the wintertime. So these squiggles, if you will, up and down during the wintertime. I'm going to primarily focus on variability in density in purple and dissolved oxygen here. But you can see that it's worth noting the variability in density is closely driven by the variability in salinity and to a lesser extent by temperature. And you can, I think of this pattern as a shift towards low density and high oxygen conditions during wintertime that's being interrupted by a period of relaxation back towards more summer-like conditions. So you can see that here in the beginning of October, November, we see this evolution towards low density and high oxygen, which then becomes interrupted by this pause in that trend or even a relaxation back towards high density, low oxygen conditions. And then right around the beginning of January, most years, we see a return to that evolution towards high oxygen, low density. And then eventually in the later spring months, February, March, we see the sort of permanent return to summer conditions for the year with some variability. We can also note on these plots that there's just a large degree of variability in general during wintertime, which you can see in the spread of the gray time series during winter compared to the summertime. So it caught our interest. And one interesting thing about these patterns too is it's not just an artifact of the composite process. So if we examine individual years time series, so on the left here is those same composite cycles, and then moving from left to right, I've just plotted the individual years of each variable after that. We can see a similar pattern is observed most years with slight variations in the timing and magnitude of these fluctuations. It's most clear in density here, and it forms this, what I call the wintertime density W. So these two periods of low density conditions interrupted by this relaxation towards high density. You can see in most of these years. And there's a strong inverse correlation between density and dissolved oxygen. Unfortunately, we only have 3 years of the oxygen on record. So yeah, it's an unexpected pattern, and it raised the question, what's going on here? Which leads to part 2, investigating the physical drivers of this intermediate depth variability pattern. So here I'm going to look at lateral advection, the influence of horizontal currents, and the influence of coastal upwelling and downwelling. So I'll be showing a lot of plots similar to this, bivariate plots with dissolved oxygen on the y-axis and density on the x-axis. On the left here, the data points are colored according to month of the year, with the warm colors indicating the summer months, cool colors the winter months. And on the right, I've color-coded according to the direction of the local current velocity at 100 meters of the shelf break, with the warm colors, where's my pointer, representing flows towards the south, southeast, and the cool colors towards the north, northwest. And then the size of the scatter points denotes the speed using the convention and the legend there. So speeds ranging from 5 to 20 centimeters or so per second. And we can see that these low oxygen, high density values that we see during the summer correspond to southeastward flow or weak northwestward flow, whereas the high oxygen, low density values observed during the winter correspond with these strong northwestward flows, the large blue scatter points here. And we can see that the broad range of winter values associated with the wintertime variability pattern are related, perhaps not to the direction of the flow. For the most part, it's always oriented towards the northwest, but maybe to the strength of that flow. You can see the scatter points are generally lower throughout the sort of center of the mass here, and they're the higher velocities up towards the top in the very high oxygen conditions. And this relationship is consistent both on the seasonal and subseasonal time frame. So on the left here is the full data set that we just looked at, and on the right, I've subsetted only the winter data, or basically I've just put the summer data in gray. And we can see a few things. We can see that the wintertime values really account for the majority of the observed range in the data, which isn't all that surprising. If we go back to the composite cycles, there's just a small range of values that occur during summertime compared to the larger range in the winter. But we can also see that the relationship between density and oxygen and the current velocity is maintained during those winter fluctuations. So in other words, the wintertime fluctuations in density and oxygen coincide with subseasonal fluctuations in northwesterly flows. So during wintertime, we're seeing these reversals in the current towards southward flows, or just a weakening of the northwestward flow, and then that's corresponding to the decrease in oxygen and increase in density. And this relationship.
Ben,
Yep.
just a quick reminder, 2 minutes.
Okay, thank you, Dan. I will try to hurry up. So this relationship is unique to these intermediate depths. Really quickly here, if we look at other depths of the shelf break in the top row and the nearshore in the bottom row, we see that there's not that separation according to the current velocity. It really is unique to 100 meters at the shelf break and at the nearshore as well, these intermediate depths, although the specific relationship is actually different here. It's flipped, but I'm not going to get into that. The second mechanism we've looked at is upwelling and downwelling. So it's a similar plot here, the same data, oxygen density, but now colored by month again on the left, and the back-end upwelling index, which is a measure of upwelling strength on the right. And we can see that those low oxygen high density values coincide well with the summer upwelling or upwelling index, whereas the high oxygen low density values in winter correspond to a large downwelling index. Again, if we look at the winter subset, this relationship is maintained. So suggesting that these regular subseasonal fluctuations in both the alongshore current and downwelling appear to drive this significant density and dissolved oxygen variability during the wintertime. And one last thing I'd like to mention is that this wintertime variability also has potential implications for the marine carbonate system and acidity stress. So one other thing we've done is we've generated estimates of aragonite saturation state by applying a regional MLR model that's been developed by Alex Hare and Wiley Evans of the Hakai Institute. For those not familiar, the saturation state represents the favorability of a mineral to dissolve in solution, and it's often used as a proxy for acidity stress. So if the saturation state is below 1, which I've marked on these plots here, those conditions are undersaturated and might cause acidity stress for calcifying organisms. These are similar plots here, but instead of oxygen on the y-axis, it's saturation state. And we can see that the wintertime northwestward flows and downwelling are really driving that saturation state above 1, or taking it from undersaturated to oversaturated conditions, which we think is an interesting result. In summary, we've documented an unexpected recurrent subseasonal variability pattern, the shelf break of Queen Charlotte Sound. This pattern is most evident at intermediate depths and appears to be closely related to subseasonal fluctuations in local current transport and downwelling strength. And it drives an injection or withholding, depending on how you want to look at that, of oxygen to intermediate depths, and may also result in a shift from undersaturated to saturated conditions. Understanding why the current transport and downwelling is undergoing these subseasonal fluctuations, I'm still not clear on that. Some thoughts might be that's related to large-scale atmospheric wind patterns. The local velocity is responding to local winds. I didn't have time to show that, but it is. Or possibly buoyancy-driven coastal currents and or local canyon dynamics. So thank you very much for your time.
Okay, thanks, Ben. And for the viewer online, and if you have any questions, please feel free to leave them in the chat or the QA box. The speakers are also monitoring the chat or the questions, and they can respond to you online. I got a very quick question, and you mentioned the buoyancy-driven current, and then have you looked at the freshwater input effects, particularly to the nearshore region on the variabilities?
Yeah, I think there's clear signs of those freshwater inputs, just the salinity metrics, especially at the shallower surface, shallower levels, they're consistently biased towards lower salinity values. There's been other work that's been done there using ocean gliders to look at the freshwater influence in the nearshore. So yeah, there could be that, and then also the coastal current on the outside of Vancouver Island, I think might well be involved, and I think that's related to buoyancy effects as well. But
yeah. Okay, thanks. Let's move on to our third speaker. Our third speaker is Professor Susan Allen, and from UBC. She's going to share with us controls on exchange through a tidal mixing hotspot at an estuary constraint. Over to you, Susan.
Just setting up the screen here. Okay, view. Hello, everyone. It's wonderful to be back at CMOS. I gave some very, very preliminary results on this tidal mixing hotspot work at one of our very first online CMOS conferences, and I'm happy to come back with some very strong results. I'd like to thank my co-authors, 3 postdocs, and our software engineer. Back when I was a graduate student, which was truly a long time ago, in the lab, my supervisor was working on what happens to gravity currents if you put turbulence on them and if you bubble air through them. And he found that you significantly inhibited the flow of the gravity currents by mixing them with the gravity current going the other direction. So my question is that actually going on in the real world? Can we see that when we go through a very complicated turbulent region in a real situation? So I'm going to tell you a little bit about the model I'm going to use so we can see this complicated real system, show that it actually reflects reality. And then I'm going to go into some analysis, and our analysis of estuarine circulation here is a little different than what's standard done. And I'll talk a little bit about how it's different and complementary to what's usually done. And I'll finish with some results. Okay, so we're here in the Salish Sea. So we've gone a little bit south from where Ben was. And this region is very freshwater dominated. And most of that fresh water comes in from the Fraser River, which enters here. The major connection to the open ocean is down here at the mouth of Juan de Fuca. And in between, we have this region of islands, the Gulf Islands here and the San Juan Islands here. And this is a constricted area with large tidal mixing. We use a NEMO model to model this region. So the gray box shows the model domain. This is a full baroclinic model coupled to biology, though I won't talk about the biology today. It's forced with realistic atmosphere, rivers, and boundary conditions. The horizontal grid spacing is about 500 meters by 440 meters. So we are resolving most of the stirring in the horizontal. The vertical grid spacing is 1 meter near the surface and 27 meters at depth. In most regions, this is enough to resolve the vertical mixing by the grid, but not completely in the tidal mixing area. It's about 75% of it. And the underlying vertical mixing is a K epsilon GLS turbulence model. Okay, so here is some evaluation. We've done more than this, but you don't want to look at 100 evaluation plots. So the data here is courtesy of Ocean Networks Canada, and it's shown in green. We have nodes at the bottom at 4 different places here. And in each one, I'm showing you the salinity on the left and the temperature on the right. The pink is the model. And so you can see at depth, we are picking out at the right time the deep water renewals and the slow decrease in salinity over time. At the east node, which is here, we're getting not only the change in salinity, but also the fluctuations in salinity and how those change through the year. So the model is reproducing the structure of the flow that is coming into the Strait of Georgia. Okay, so let's look a little bit at the system. I run a red line here through the center of the Strait of Georgia and out Juan de Fuca. This is the Thalweg, the deepest line. If we look at that, and here I'm starting at Juan de Fuca, here's Juan de Fuca. If I look at a vertical cross-section through that line, we can see this region here, the mixing region, which Paul LeBlanc talked about many, many years ago. But we can also see it as a kind of a gravity current system. Here is the dense water trying to get into the Strait of Georgia. Here's the fresh water trying to exit out to the ocean. And in this region between Victoria Sill here and Point Roberts here, we see a lot of almost vertical isohalines showing that we have a great deal of mixing in that region. Okay, so let's zoom in here. So this is our northern end of our mixing region, the Point Roberts line just south of Vancouver. And here is the Victoria line here. And of course, this is a real system, so it gets complicated. We have Puget Sound here down to the south and a little tiny Deception Pass here. Okay, so this is a kind of traditional view of estuarine circulation that I teach in the estuaries course at UBC. And so we can think about the fresh water coming in from the Point Roberts end. As it moves through this region, it trains a lot of deeper water, which is called the efflux, which comes in and exits in the surface layer. We have the deep water coming in from the ocean, and a small amount of fresh water mixes into that. Okay, to evaluate this in a model, why am I not going to the next slide? There we go. We have the other thing, which is the tides. And the tides complicate the calculation of the fluxes in a numerical model because you can't just average. If you just average, you don't take into account that the water on the tides isn't exactly the same as it goes back and forth. And so you've got to get smart. One of the ways to do this is to use salt as a tracer of the flow, but that gets complicated when you've got multi-connections. So we're going to use a different way of doing that is we're going to actually follow fluid parcels using Ariane. Ariane is a Lagrangian tool that actually allows you to be quantitative. So it takes all the flow going through a transect and breaks it into parcels and tracks those parcels until they reach the edge of the region back to the same transect or into another transect. The parcels absolutely follow the resolved flow of the numerical model, and they mix as they move. So any of the subgrid scale mixing actually changes the salinity, temperature, and anything else in the parcels. And we track parcels from one transect to another. So this gives us a slightly different view of estuarine circulation. First of all, we're talking about flow through a region. So I have made these arrows continuous from one end to the other because that's how Ariane looks at this. And as we go through this flow, we actually have changes. So we have a baroclinic exchange flow that goes through the region. In this region, we also have a barotropic flow because we have flow from the north right through the system. We have loop flows, which we call the efflux and the reflux. And then we have tides, which are loops of less than 24 hours. Of course, this isn't actually what the flow looks like. The flow looks like this for any given parcel. There's an incredible amount of turbulence stirring in this region, and it takes about 2 weeks for parcels to move through this region. I'm going to focus now on the pink parcels, which is the baroclinic flow coming near surface, buoyant baroclinic flow, and the purple one, which is the deep water coming in. So this is the baroclinic exchange flow. And of course, I drew this in 2-dimensional. These curlies are 3-dimensional, not 2-dimensional. Okay, back to what we were doing here. We have this gravity current, and Paul Linden showed that how far the gravity current got through this region was dependent on the density difference between the two water masses, and was inhibited by a mixing which he quantified with a Richardson number. We can't easily have such a simple picture of gravity currents. It's hard to talk about a gravity nose. And so here we're going to look instead at the flux through the system, this exchange flux due to these two gravity currents. And we're going to look if that can be explained by a density difference and inhibited by mixing. So here is a picture of the baroclinic flux. On the left, I'm showing you 2 years. On the right, I'm showing you 6 months. In the bottom plot, I'm showing you the density difference between Victoria Sill and Point Roberts. That's the density difference across this region. You can see that it is low in the winter times and high in the summer times. And that's for 2 different reasons. In the summertime, the Fraser River is flowing strongly, mainly in the spring here, because of the snow melt. And then here in the late summer, the density difference is large because we have dense water that upwelled on the coast that's gone into Juan de Fuca. And so this gives us a very long, broad summer time where we're pushing a high density gradient. And so we see in the summertime, the baroclinic flux is really strong. If I jump over here and look at things that I can see on a smaller time scale, in the green here is the low pass tidal speed. So this is a measure of how strong the tides are, and is showing our measurement of mixing. Stronger the tides, the more mixing. And we can see that there's a very strong negative relationship here. When the tides are strong, the flux is slow. When the tides are weak, the flux is strong. And so we have exchange flow driven by density difference, inhibited by tidal mixing. Okay, and so here is a plot.
Just a 2 minutes reminder.
Yeah, 2 minutes, yes. So here's a plot showing that this works really well and explains about 95% of the variance. So the blue is the theory and the orange is the line you just saw. And on the right, you've got a 1-to-1 plot showing how strong the relationship is. I want to show you one more thing that you can get from this analysis in these last 2 minutes. And so here on the right, on the upper right, I have a cross section here at Point Roberts. And here on the lower right, I have the cross section at Victoria. And these are the mean over the year. And we can see how the water on the mean flows. Of course, it's actually more complicated, but generally the surface water is coming out of the Strait of Georgia on the right, heading out to the surface on the right at Victoria Sill. But the other interesting thing is we also get intermediate water that makes it from Strait of Georgia out to the Victoria Sill. The intermediate water coming from Victoria Sill and the deep water coming from Victoria Sill end up on the right in the Strait of Georgia, and deep in the trough is where the deep water comes in. However, from Victoria Sill, the real pattern here is that that water is flowing from over the 2 troughs, as opposed to really tightly on the right. Okay, so quickly in summary, a Lagrangian view of estuarine exchange is complementary to the Eulerian view. I haven't shown it, but Camryn will show that in a little while. It's more flexible for complicated systems, and it includes the full three-dimensionality of the exchange flow. I showed here that the baroclinic exchange flow is determined by the density difference in the Richardson number based on the tidal velocities. That the outgoing flux includes both surface and intermediate waters, and the incoming flux includes both intermediate and deep waters. And laterally, the fluxes into and out of the Strait of Georgia and across Victoria Shield show strong impacts of the Coriolis force and the local bathymetry. Thank you. Dan, you're muted.
Yeah, thanks, Susan. Now, if you have questions, and then please type your questions in the chat or the Q&A tab online. I haven't seen any questions online. Oh, there's one.
Okay, so the first question is, don't we usually think of estuarine exchange being driven by mixing? However, other locations is that there is substantial baroclinic or rotational topographic control. Have you ruled that out here? Okay, so estuarine exchange in shallow systems and in partially mixed estuaries certainly transfers salt by mixing. And so that is, in other systems, a dominant part. Out of the Strait of Georgia, the dominant is the baroclinic exchange. At the Victoria Sill, the mixing is also important. And so one thing to realize from the analysis I just gave you, I talked about a component of the estuarine exchange. And so I talked about the gravity current exchange, but there's also a component of mixing. Okay, for Susan, how does Ariane take into account horizontal or vertical mixing? So it explicitly takes into account all the resolved mixing. And one of the nice things about modern numerical models is that our largest mixing eddies, our largest turbulent eddies, are actually resolved. And so most of the large eddies are resolved, and so Ariane directly takes those into account. The subgrid scale mixing is taken account by basically starting the molecular true mixing as opposed to stirring at the grid cell. And so it takes into account and tracks for you the changes in salinity as you follow a fluid parcel due to irreversible mixing.
Okay, those are great discussions. So let's thank Susan again for her great presentation. I will leave the discussion continue online. If you have questions, please leave them in the chat. I think the speaker is going to answer them online. Our next speaker is Jamie Daniel from UVic, and she's going to talk about rip current observations on the west coast of Vancouver Island.
Okay, yeah, I'll just get my screen share set up. Okay, can everybody see my screen?
Yeah, it looks great.
Okay, awesome. All right, so I'm Jamie Daniel. I am a master's student at UVic, supervised by Johannes and Jody. And today I'm going to be talking about some preliminary rip current observations on the west coast of Vancouver Island. Specifically, our study area is focusing on the Long Beach unit of Pacific Rim National Park. This is a long sandy beach that's exposed to the Pacific Ocean swell as well as breaking waves. And as a result, it is a very popular surfing location. So we kind of focused on two main areas of the beach. The first is Long Beach up at the north end, and then Wickeninish Beach at the south end. So rip currents are strong seaward directed flows that begin near the shore and extend out through the surf zone. They are very fast moving and can quickly transport surfers and swimmers out of the shallower water and into deeper water. And as a result, they are considered one of the most dangerous coastal hazards. Specifically at Long Beach, they have been responsible for injuries, water rescues, and unfortunately even deaths. So they are definitely a hazard worth studying. Rip currents are generated by variations in the height of breaking waves. And these can be caused by bathymetric variations such as sandbars and troughs, or by structures like rocks or breakwaters. Specifically at Long Beach, there's a rock known as Lovekin Rock where many rip currents have occurred. So these variations in breaking wave height cause an alongshore pressure gradient, which results in longshore currents that converge, and then the result is an offshore flowing rip current. And as well, rip currents are greatly affected by the tide, the tidal elevation, and also by the incoming wave field. So during this study, three main observational methods were used. The first was GPS drifters, which are pictured here. They contain a GPS and an accelerometer. And from the GPS, we can get measurements of rip current speed and trajectory. And from the accelerometer, we can obtain measurements for nearshore wave parameters, such as significant wave height, peak period, and peak direction. So during August of 2023, 3 deployments took place at Long Beach near Lovekin Rock. And so here I have the tidal elevation and the wave parameters for those 3 deployments. And we can see across all 3 deployments, the tide level was very similar, around the mid-tide level. And our wave conditions were very similar as well. And in fact, the wave conditions were fairly calm during these deployments, as significant wave height did not go above 1 meter. So this is an example of the GPS tracks that we can get from these drifters. This is from the first day of deployments at Lovekin Rock. And so along this light gray shading here shows the coastline. This is Lovekin Rock here. And so the drifters started in the rip current along the side of the rock and then flowed out towards the sea. And so this is for a 15-minute deployment with 2 different drifters included, and they are colored by the drifter speed. And from the time series below, we can see that the rip current speed was fairly low, with an average speed of about 0.24, 0.22 meters per second. Occasionally, the speed increased to about 0.6 meters per second, and there were a couple of short time periods where it did reach over 1 meter per second. But overall, a very slow-moving rip current by rip current standards, and that sort of matches with how calm the wave conditions were for those deployments. So because we get accelerometer measurements, we can get vertical displacement measurements from these wave drifters. And from there, we can calculate a wave energy density spectrum and the corresponding wave parameters. So on this plot here is an example of a wave spectrum from one of those drifters' deployments. And we can see that the high frequency tail of the spectrum follows the f to the -4 slope that we would expect from a wave spectrum. We can compare our wave parameter measurements to those of a spotter wave buoy located 1 kilometer offshore of Long Beach. And so we see that they are fairly close. The drifters measure a higher significant wave height by about 9 centimeters. And as well, the drifters have a much larger spread in their significant wave height measurements. And from that, we can kind of see that these wave drifters show the short-term variability of the surf zone. The second observational method we used was an acoustic Doppler current profiler, which was deployed for 1 week at the end of October at Wickeninish Beach here at the south end. And so on the left, we have tidal elevation, alongshore velocity, and cross-shore velocity time series profiles. And I've indicated this area over here with the red box because we see more wave action in the pressure data during that time. And we can also see we have stronger alongshore and cross-shore velocity variations. And when we take a closer look, that is indeed what we see. The red indicates a positive velocity. So for a cross-shore velocity, that is moving offshore, so the direction we would expect a rip current flow to occur. And we can see we sort of have these alternating periods of very strong offshore velocities and stronger onshore velocities. And in doing a quiver plot of the flow direction over the ADCP, that is indeed what we see. We see this sort of background flow of smaller arrows. So a kind of a background onshore velocity. And then we have these intermittent periods of very strong offshore velocities. which is what we would be expecting a rip current flow to show up as in this data. And our final method is coastal video monitoring. So an infrared camera has been set up long-term at Wickaninnish Beach. And the video camera records 10-minute video segments. Then the images in these video segments are then averaged over the 10 minutes. And the idea with this method is that if there is a rip current consistently occurring in this area during that time period, it will show up as a region of low intensity, so a dark region between regions of higher intensity, so lighter breaking waves. So we have two images here from February 25th and 26th of 2023. In the first image here, we can see this kind of pattern of a darker streak between lighter regions of breaking waves, and that is indeed what we are looking for when we're trying to identify rip currents in these images. And then in the next image here, we can see that we don't see that signature of a rip current. So when we're looking through these images trying to identify rip currents, we are really looking for a signature like in the first image here. And so this is a plot of the tidal elevation over a week from February of 2023. And so these gray bars here indicate times when rip currents have been spotted in these images. And so when we plot those times over this plot of tidal velocity, we can see a pattern emerge that rip currents are being detected in these images during the rising or the high tides, and not so much at the low tides. So going forward, ideally what we would do is also take into account the wave parameters and plot similar plots to this, and also do these over a longer period to get a more definitive idea of when these rip currents are occurring. And so just to summarize, we have seen some preliminary observations of rip currents in the Long Beach unit of Pacific Rim National Park. 3 main observational methods have been used. The first is Lagrangian GPS drifters, where we get measurements of the rip current speed and trajectory, and we can also calculate near-shore wave parameters. The third is an acoustic Doppler current profiler, where we can see velocity profiles and try to determine when we're getting that strong offshore flow of a rip current. And the third is coastal video monitoring, which provides us with direct imaging of rip currents. And from there, we can determine when exactly are we seeing rip currents in this video frame and what's going on with the tide and the wave field during that time. And so the next step for this research is to continue the work being done and come up with get a more clear idea of how exactly rip currents in Pacific Rim National Park are being modulated by the tidal phase and wave field. So thank you very much.
Thank you, Jody. And we have about 3 minutes for question. If you have any questions, please feel free to leave them in the chat or the Q&A tab on the platform. Jamie, I got a question about your coastal video monitoring system, and it seems a very interesting system. I'm wondering, what is the swath, like the coverage of the video camera?
I don't know the exact region that it covers, but I think it's about maybe about 10 meters along the beach. I'm not sure about how far out it looks.
Could you expand on what is direct imaging of rip currents?
By that, I just mean we can detect the rip currents in the images so we can visually see them occurring. Whereas more in the other observational methods, we don't see the rip current occurring. We kind of look at the data and use that to determine if there's a rip current happening.
Okay. Thanks. Let's we have 2 more minutes for next speaker. I'm going to leave the session open, and then if you have questions, please leave them in the Q&A tab. While we're waiting, let me introduce our next speaker. Cameron, can you share your slide so then we can start in about 1 minute?
Yes, you should probably be able to see my screen now.
Yeah, that's look great. Let's just wait 1 more minute and then we introduce you. You can get started.
Sounds good.
Okay, our next speaker is Camryn Stang, and she's from UBC. She's going to talk about the estuarine exchange in Salish Sea. Over to you, Cameron.
Great, thanks, Dan. So yeah, hi everyone. I'm a PhD student working with Susan Allen at UBC, and today I'll also be talking about the dynamics through the San Juan Gulf Islands region, but more specifically looking at how the dynamics are different between the different interconnected pathways. Okay, so I'll start with some background. The Salish Sea is a highly productive coastal ocean, which consists of the Strait of Georgia, Puget Sound, and then opens up to the open ocean, mainly through the Juan de Fuca Strait here. The main point of exchange between the inner basin, which is the Strait of Georgia, and the open ocean is through the San Juan Gulf Islands region, which is shown in the pink box on this map here. And in this region, the water branches into 3 different straits, Haro Strait, San Juan Channel, and then Rosario Strait. Haro Strait on the left here is the largest and the deepest of the 3 channels. San Juan Channel, which is in the middle, is the smallest and the shallowest of the 3. And then Rosario Strait on the right is not quite as wide and quite a bit shallower than Haro Strait, but we'll see throughout this presentation that it does have an important influence on the dynamics in this region. So the dynamics in this region are quite complex because of this branching flow and also because there are various different islands and it has complex bathymetry. And then the combination of the bathymetry with the tides creates lots of mixing, making the transport through this region even more complicated. Some motivation for this work is that previous studies have shown higher dissolved carbon and lower pH in the Strait of Georgia than on the outer coast of Vancouver Island, which essentially corresponds to higher rates of ocean acidification happening in the Salish Sea than in the open ocean. So to try and explain and understand some of these observations, it's important to first understand the transport through this region, so determining how water is moving into and out of the Strait of Georgia, which is what I'm looking at here. And then to do this, I'm using the model Salish Seacast, which the model domain is shown in the gray box on this map. So now I'll just talk about a little bit more about the model. I mentioned I'm using Salish Seacast, which, as Susan said, is a 3-dimensional coupled physical, biological, chemical model that's based on NEMO 3.4 framework. There's about 500-meter horizontal resolution, which corresponds to 398 points in the X direction and 898 points in the Y direction. There's variable vertical grid spacing with smaller boxes starting at 1 meter near the surface where there's more variability and reaching larger boxes of 27 meters in the deep where the changes are more gradual. And the vertical mixing is based on the K epsilon GLS scheme, and the model includes tides and has hourly output. So for my analysis, I, like Susan, use Ariane, which is a Lagrangian particle tracking algorithm that uses output from Salish Seacast. So Ariane releases particles and then it interpolates the velocity at each time step for each grid cell in the model, and then it calculates the corresponding flux represented by each particle. Ariane has 2 different modes. There's qualitative, which tracks particles as they move, so you can get a trajectory and can follow particles and see exactly where they're moving. This is useful to see the exact path particles are taking. So like you can see in this video, I chose to release particles in Haro Strait and then track them for 28 days. The back and forth motion that we're seeing is tidal sloshing, and we can see that in the San Juan Gulf Islands region, particles tend to get hung up and are moving a lot in between the different straits, and only a few are making it all the way through into the Strait of Georgia. So since there's all this turnaround and only a few particles are making it all the way through, to get a better idea of the transport through this region, we need to release lots and lots of particles, which becomes quite computationally expensive when we use the qualitative mode of tracking. So it's more useful for the purposes of my analysis to use quantitative Ariane, which rather than tracking the entire path for each particle, it just tracks where the particles are starting and where they end up. So in this picture, you can see that we have a starting boundary where you can release many, many particles all throughout the boundary. And then the information for each particle is tracked once it reaches another boundary, but we're not actually getting information about what's going on in between. So this allows for many more particles to be released on the order of tens of thousands of particles. And you can specify, or like you can release particles all throughout the boundary rather than having to specify exactly where they're starting. And then Ariane also has the benefit of being able to run simulations forwards and backwards in time. Where you run forwards in time, you can release particles and see where they're moving to. And when we run backwards in time, we can see where particles at a boundary are coming from. So for my experiments, I have two different configurations. I run what I call the split region experiments, where I split the San Juan Gulf Islands region into two subregions. We have the eastern Juan de Fuca subregion, which has a boundary at Victoria Sill and a boundary through each of the three straits. And then to close the region, we have one at Admiralty Inlet and Deception Pass. And then to the north, we have the San Juan Gulf Islands subregion, which has the same boundary through each of the three straits, and then one through Point Roberts, and then one through the Gulf Islands. To get a better idea of what's actually making it all the way through this region and in between the Strait of Georgia and the Juan de Fuca Strait, I run a full region experiment where I use all of the outer boundaries shown in the red lines and then let particles through one channel at a time, having a boundary at the other two. So for the example shown on this map, I have a dotted green line through Harrow Strait. So for this configuration, I don't actually have a boundary here. So anything moving between the north and the south must be going through Harrow Strait since there's a boundary at the other two. And then I run the same thing for each of the other two straits, where it would open up this boundary and then add a boundary where that dotted green line is at Harrow Strait. And then to get a time series of water transport, I run daily simulations where I release particles every day for 4 years from 2018 to 2021. Before we get to the results, it's important to discuss some model evaluation. So this plot shows some current data for the U velocity on the left and V velocity on the right from 3 current meter moorings and compares them to the model. The top row is for current meter near Boundary Pass, which is in the middle of the San Juan Gulf Islands region. The middle is for one near the Victoria Sill boundary, and then the bottom is for one near the Point Roberts boundary. The observational data is in gray, and then the blue is the predicted velocity from the closest point in the model. Generally, the model well represents the velocities. We can see that the tidal cycle in velocities is captured, and overall there's pretty good agreement between the observations and the model. The model does slightly underestimate the velocities in some places, most often in Boundary Pass, but generally all the key features are still reproduced, so it's sufficient for the purposes of my analysis. All right, so now I'll just get on to some results. This plot is from the split region experiment to examine cross-sections of water transport going to and from each strait. This is based on releasing particles at the Victoria Sill boundary, which is shown in the black line on this map. And the bottom 2 rows are based on forward seeding, so looking at where the particles are going to. And then the top 2 panels are looking at where the particles at Victoria Sill are coming from. And then for both the forward and backward seeding, I have the monthly average transport in both January and June of 2018. So for the backward seeding, we can see that the transport going from each of the straits to Victoria Sill is more concentrated at the surface, which is consistent with the estuarian circulation in the region, moving surface water away from the Fraser River, which is in the Strait of Georgia, and out to the open ocean. The majority of the transport is coming from Harrow Strait, and there's higher transport from all the channels in the summer compared to the winter, which is associated with the higher freshwater outflow from the Fraser River during that time. And then to balance the surface outflow, the deep water is moving into the Strait of Georgia, which we can see in the cross sections from the forward seeding. And again, the majority of the transport is going to Harrow Strait, with now even less going to Rosario Strait and San Juan Channel. And then from these cross sections, we can see that there's a lot more southward flow coming from Rosario Strait and San Juan Channel than there's northward flow going to each of these 2 straits. And this suggests that the southward flow is dominating through these to these 2 channels, and that's especially prominent in the summer. Now moving on to the full region experiment, this is now looking at not what's making it to each strait, but what's actually making it all the way through to another boundary on the other side. And this is the southward transport, so looking at what's moving from either the Point Roberts or the Gulf Islands boundary down to Victoria Sill or the Admiralty Inlet boundary. The top panel is showing the water transport, and we can see that the Haro Strait in blue has the highest transport, followed by Rosario Strait in purple, and then San Juan Channel in green. The transport through all three straits follows a seasonal pattern with higher transport starting in around May and lasting to about October, and then lower transport in the winter months. The bottom panel is showing the proportion of the total southward flow moving through each of the straits. We can see that the proportion of the total transport moving through Rosario Strait and San Juan Channel is increasing during the summer in all 4 years, with Rosario Strait making up about 15% of the total southward flow in the winter and about 35% in the summer. This corresponds to proportionally less water moving through Haro Strait, which suggests that even though the transport through all three straits is increasing in the summer, the amount that's going through Rosario Strait and San Juan Channel is increasing proportionately more than that's going through Haro Strait. So this seasonality in the water transport corresponds to the seasonal cycle of the Fraser River discharge, which is shown in the dotted black line on this plot. And we can see that the discharge is increasing typically around May when the snow begins to melt. And then I'm also showing the river discharge for the Puget Sound rivers, and it has almost the opposite seasonal cycle of the Fraser River, where it's lower during the summer and higher in the winter. And this is because the rivers in Puget Sound tend to be rainwater fed rather than glacially fed like the Fraser River, so they're highest when the rainwater is the highest. Now, plotting that with the proportion of southward flow moving through Rosario Strait, we can see that in general, the proportional increase seems to be well correlated with the river discharge from Puget Sound. So for example, we can see that the periods of lower proportion going through Rosario Strait seem to coincide with the periods of increased river discharge from Puget Sound. And the times that we're seeing that the proportion doesn't decrease, even when the Puget Sound rivers are increasing, is when the Fraser River is dominating, so we don't see the influence of the Puget Sound rivers. And this suggests that since the discharge from the rivers in Puget Sound comes through Admiralty Inlet, likely they are blocking some of the water transport through Rosario Strait. And the Fraser River is the dominant freshwater source. Over 65% of the freshwaters that the Salish Sea is coming from the Fraser River. So it is the Fraser River that's causing the seasonal increase in the water transport, but the proportional increase through Rosario Strait is likely because of the influence of the Puget Sound rivers.
Camryn, just 2 minutes remaining.
Great, sounds good. Thanks, Dan. And then we can also examine the exchange between Puget Sound and the Strait of Georgia by looking at the water transport between the Admiralty Inlet and the Point Roberts boundaries. So the top plot shows the southward transport, while the bottom plot shows the northward transport. And we can see that pretty much all the southward transport is coming from Rosario Transport, while all the northward transport is going through Haro Strait. And then I've also done balances through this region and compared them between January and June 2018. So from these balances, we can see that there's very little northward flow going through Rosario Strait and San Juan Channel in the winter, and even less so in the summer. This suggests that the southward transport is dominating through each of these channels, and the seasonal increase in the summer prevents essentially any northward transport through these channels. So even though we saw just a small amount of transport in the split region cross sections, the amount that actually makes it through these channels and into the Strait of Georgia is even smaller. That means that essentially all the northward transport into the Strait of Georgia is through Haro Strait, which we can see here, and we can see that the summer transport is almost 3 times that of the winter transport. And then comparing that to the southward transport, we can see that in the summer, there's much more northward transport going through Haro Strait than there is southward transport. So to summarize, some of the key points are that there's a larger proportion of southward flow going through Rosario Strait in the summer, which is likely because of the influence of the rivers in Puget Sound. And then we saw that the majority of southward exchange between the Strait of Georgia and Puget Sound is through Rosario Strait. And we saw that there's predominantly southward flow through Rosario Strait and San Juan Channel, while the majority of the deep flow is going through Haro Strait. Thank you.
Thanks, Camryn. And we have about 3 minutes for questions. If you have any, let's start the question. Camryn, are you able to see the question online?
Oh, sorry, no, I can't see them.
Let me put a link if you're. So this is the link. The first question is, why do you need Ariane for this analysis? From Jody Klymak.
So Ariane, there are like multiple different ways that you could be looking at the transport through this region. Ariane is useful because if you were like another method is looking at like the cross sections and then doing calculations just based off the cross sections. But as like I showed in some previous slides, what's actually making it through the cross section is not actually what's making it all the way through to the strait, and so it's not like capturing actually what's moving between the Strait of Georgia and the Juan de Fuca Strait. So with Ariane, when we can run these simulations and track particles, we can get a better idea of what is actually making it all the way through the area.
There's another question. So I'm going to read a question, net result and the presentation. I have a question about using Ariane. I wonder if between two sections, the parcels start at the same time, but could arrive at different time. Could you clarify how the transport calculation was not affected by the different traveling time?
Sorry, I'm just trying to wrap my head around the question. I think so the particles, it's okay if they have different times. I run the simulations for long enough that the majority of the particles reach another boundary. Ariane has a classification. In Ariane, there's a classification of particles that don't reach another boundary, and they're called lost. And I run the simulations for long enough where the lost particles are extremely low. So it's okay if they have different transport times because I run it for long enough. If particles are moving faster, they'll hit a boundary and then they're removed from the simulation. They're no longer being tracked and they're just kind of like taken out as soon as they reach another boundary, whereas the simulation is still going on for the particles that are still in the region.
Hey, thanks, Camryn, for the great presentation. Let's continue the discussion online. If you have questions, please feel free to type in the Q&A tab. Our last speaker is Guoqi Han, Senior Research Scientist from IOS DFO. He's going to share with us about extreme sea levels on the Canadian Pacific coast. Guoqi, can you? Oh, I saw Guoqi is sharing the screen. Over to you, Guoqi.
So, Shiliang, can you see my presentation?
Yeah, it's in full screen mode and I can hear you well.
Okay, great, thanks. Yeah, okay. So I'm going to talk about extreme sea levels on the West Coast for this century. And my course is Jing Lu, Thomas James, and Connor Brewery Green. So as we know, mean sea level has been rising. And as the mean sea level rise, the Pacific coast of Canada, we experience more frequent coastal flooding. So we need to improve knowledge about extreme sea level for planning and management of coastal infrastructure. And right now, the main operational storm surge forecasting is from a backtrack model for the entire West Coast of Canada. Also, there are other bioclinical models like Salish Sea, forecasting. And so this study is to provide improved estimates of extreme sea levels in the 21st century and understand some major forcing factors as well. So we've used the ocean model and tidal gauge data. And here you are looking at the model domain. This is NEMO model with 136-degree horizontal resolution. And we including tidal forcing, wind forcing, and freshwater runoff, and heat flux. So it's fully bioclinical circulation model. And the wind is by F5 hourly products and open boundary condition is from 1/12 glorious global model output. So river runoff is Morrison et al.'s climatological monthly means. And we have selected 10 tidal gauge stations around the coast. Those are the long-term tidal gauge stations operated by Canadian Hydrographic Service. So we will evaluate the model also, against the tidal gauge data at those stations. And we have run model from 1993 to 2021. And So where we use the same, where we use the tide gauge data over the same period. And we have done the extreme sea level analysis using Gamble approach. And here, so we are looking at the 100-year return level. And so the vertical coordinate is return level, and the horizontal coordinate is return years. Blue observation rate is model, and the shaded area indicating the 95% confidence level. So we can see visually an overall model seems in good agreement with observation. And so if you look at 100-year return level, and the variation is from 2.1 meter at Victoria Harbour to 4.4 meter at Prince Rupert and Queen Charlotte City. The model underestimates by 20 centimeter on average, and this is the total extreme sea level. So including tides and all factors, causing factors. And now we look at the non-tidal sea levels. And so here again is 100-year return level. And if we look at the range, the values change from 1 meter at Victoria Harbour and to 1.8 meter in the northern stations. So that's Prince Rupert and Queen Charlotte City. The model now underestimated by, again, 20 centimeter on average. So if you look at the previous slide, including tides and the non-tidal sea level, on average for entire region, tides account for like 50% or so, and non-tidal component also account for 50% approximately. So we have looked at it further, because previous models usually said it's, this extreme sea level mostly related to tides and storm surge. But for the Pacific coast of Canada, we just decompose, this component, total sea level into a non-tidal sea level into 3 components. So one is a storm surge component, period less than 10 days, and the other is interannual variation, longer than 1 year, and in between we call intraseasonal and seasonal component. So here you are looking at this extreme sea levels from these 3 components, and for model and observation, okay? So from look at this pattern, basically, if we combine just this interannual, we just separate it into 2. Probably it's more straightforward now, storm surge and non-storm surge. So you can see non-surge and surge contributions are comparable at half of the size, okay? And storm surge contribution is really dominant at Vancouver and Queen Charlotte City. So Queen Charlotte City here and Vancouver here. And that's from the at the 10 tide gauge sites from model and tide gauges. And so we look at the models, we have did this same analysis at almost all Canadian Hydrographic Services tide gauge sites, including permanent and non-permanent sites. And so we look at this contribution, from surge component and non-surge component. So non-surge component means B plus C, okay? And so as you can see, the storm surge component is dominant in part of Hecate Strait and less so in the Strait of Georgia. If you look at along west coast of Vancouver Island, and Queen Charlotte, coast of Queen Charlotte Sound. So you can see non-surge component and storm surge component are comparable. And we further look at the potential contribution, to extreme sea level from the UNSO and from the Pacific Decadal Oscillation. So our results have already indicated the UNSO is more related, robust. So we just focus on the relationship between Nino index, Nino 3.4 index, and the extreme sea level. Okay, and so here we calculated the correlation coefficient, and if it's a solid bar, means statistically significant at a 95% confidence level. And so you really can see this non-surge component, including intraseasonal, seasonal, and interannual component, are statistically significant with El Nino index, and so that's positively correlated. And if you look at this storm surge component, then it's sort of negatively correlated, but as insignificant. So if you combine all the effects together, the storm surge, the non-surge effect is sort of reduced, so cannot be seen. Only if we separate them, we can clearly see El Nino would enhance extreme sea level. And now to the future extreme sea level. So, so for the future extreme sea level, we just consider mean sea level rise. So we first get the mean sea level rise, then we just add the present extreme sea level used as a proxy for the future extreme sea level. And here you are looking at the mean sea level rise by 21 at the end of this century, and it's for two scenarios. So the first one is a median scenario, median emission scenario. It's a shared socioeconomic pathway 245, and the other one is a high emission scenario. So it's a 585, and you can see the mean sea level rise. If you're high emission, it's relatively higher. On average, about 10 to 20 centimeter higher by the end of the century. And over they have large spatial variations. So variation is from like 30 centimeter rise to about a 1 meter rise in the northern part around the around Prince Rupert and Queen Charlotte City. Okay, so there's a large.
Just 2 minutes reminder.
Okay, thank you. And this shows the projection of extreme sea levels versus the time. Okay, and for different emission scenarios at Vancouver. So just to give you some sense, they are depending on the scenario and also changing with time, generally increase. And also there's a large uncertainty. The dashed line indicates the 95% confidence interval. So there's a large uncertainty associated with these projections. And this slide on the left shows the projected extreme sea level. It's the 50-year extreme sea level at 2100, and for the median emission scenario. So we can see the sea level change quite significantly from south to the north. Again, at Prince Rupert and Queen Charlotte City, it's much larger, about 5 meters, and this is a total extreme sea level. Okay? And so if you look at this Campbell River area, it's much smaller, so about a 2.5 to 2.5 meter. Okay, And the right panel shows how the twin year will change. So we are looking at for median emission scenario, for present day 50-year return level, and what will be the return year for the future. So as you can see, at the end of this century, present 50-year return level at most sites will be less than 10 years, okay? So in some sites could be just 2 or 3 years return. And exception is around Campbell River area. You can see actually the return year will increase initially, and then eventually will decrease. And by end of this century, will be 50-year return level will become like 30 to 40-year return level. Okay. So to conclude, present day extreme sea levels show substantial spatial variations. So from 2 meters in Strait of Georgia to about 4.5 meters in Hackett Strait. On average, tidal and non-tidal components are comparable approximately. Non-surge variations contribute substantially to non-tidal extreme sea levels, and El Nino enhances the non-surge contribution. So this is something different for the Pacific coast from other areas such as, Canadian Atlantic coast. Extreme sea levels increase in the rest of this century, except in the northern Strait of Georgia, where the first decrease and then increase, depending on emission scenarios and the geographical locations. So, yeah, some of the results have been published in JGR Oceans. Yeah, that's all. Thank you.
Thanks, Guoqi. Now let's have questions. And if you have any questions, please type them in the question and answer tab online. Guoqi, are you able to see the questions?
So I need to click the link you sent, right?
Yes.
Oh, okay. I haven't. Let me see.
So there's a question from Jody Klymak asking, do your results include glacial rebound?
Yes. So the future projection includes the effect of post-glacial rebound and also the tectonic movement. And so that's why we're seeing the big difference in the like for the northern Strait of Georgia, like a Campbell River. I think there's a land uplift there, for various reasons. And but overall, in this case, the post-glacial rebound probably is not that big effect for this region. Still there's some effect, but probably mostly it's the sediment compacting, and also the tectonic movement is more important effect affecting the land motion, vertical land motion.
Yeah, there's a second question online. Guoqi, are you able to see the questions?
Oh, the how?
Yeah.
For how will future Cascadia earthquake impact? You mean this one?
Yeah, that's the second question.
Oh, that second question. Oh, this question. That would be a very good question, a very good impact. But at this moment, I think we are not able to assess. I would say once something happened, and we have to reassess and adjust the values. And but anyway, so usually the IPCC is doing like every 5 years where do the assessment. So once there's any further assessment by IPCC, we will also update the assessment in terms of more information. But for this earthquake thing, we really needed to wait for if something happened, maybe we can adjust, but not right now. For modeling into future, can you describe how robust do you expect results to be? Well, that's really a big question. I think so. The present climate models still have large of uncertainties. And beyond this model uncertainties, there's also scenario uncertainties. And how climate change trajectory actually will go. So I guess we have to be really do due diligence exercise and to look at what's going to develop and continuously improving our projections.
Okay, thanks, Guoqi. Now it's 1:50 for my Eastern Daylight Time, and then let's conclude our part 1 of the coastal oceanography and the inland waters. Now let's thank all the speakers for part 1, and we're going to take a 15 minutes break and then continue on part 2 and part 3 of the session, where you're going to hear interesting talks focusing on East Coast of Canada and Arctic.
Thank you then.